Hello, everybody. My name is Paul Taylor. I'm an engineer at NVIDIA. I work on our GPU accelerated data science team. So we have these libraries called RAPIDS, which are GPU accelerated implementations of common data science libraries. So is anybody, this actually really helped me out because knowing like what your audience knows, I can get super technical or I can like, start from the basics, and either one is fine with me. I just need to know what you guys are familiar with. I don't want to go off in the weeds and get technical and lose everybody. So up front, is anybody, how many people are familiar with things like pandas? Like the Python library pandas? Okay, so 3. I'm not checking Slack, unfortunately, so 4. All right, so pandas. Okay, so I'll stay light on the panda side. How many people are familiar with GPU programming in general, or GPU programming? So general purpose computing on GPUs? A couple people, 5, 6. Okay, cool. And I guess everybody's normally familiar with just regular data visualization, using deck.gl, maps, that kind of stuff. Okay, so that gives me a good place to start. I'll sort of gloss over some of the low-level details of what's going on and really hit the high points. So RAPIDS is, like I said, a GPU accelerated data science library, or a suite of data science libraries. I guess a little bit about me. So this is my Twitter. I'm inlineptx on Twitter, which is a little GPU joke for people who like GPUs. And so my background is I was one of the co-authors of RxJS, if you're familiar with that library. And then I also wrote the JavaScript implementation of Apache Arrow. So, and now I work on a data science team at NVIDIA. So the RAPIDS libraries are in Python typically. And one of the fun things about Python, this is one of my favorite GIFs here, is this one, sure, except all the cookies, block. Is this little video here just reminds me so much about the ecosystem between JavaScript and Python. Is Python gets all the cool machine learning GPU accelerated stuff, and JavaScript gets WebGL, which is super frustrating for anybody who likes to program in JavaScript, especially if you do stuff in the browser, you do stuff in Node, maybe you do stuff in Electron, and you like the ability to use the same language in all 3 environments. The language itself actually does this a little bit. They don't want to add things that are in Python that would make machine learning a whole lot easier, or do make machine learning a whole lot easier. So JavaScript isn't totally blameless, but this is sort of the ecosystem we inhabit. But that said, I know there's a lot of people who still like JavaScript and still want to do it, and they want to be able to take advantage of GPUs as well. So at NVIDIA, part of our job is we don't see ourselves as doing things like writing a competing data visualization library or a competing mapping tool. Like what we see our job is building bridges to the communities where that stuff's happening. So anything that we can do to enable you guys to use the GPU to solve your problem, that's what we care about doing. So like I said, RAPIDS is traditionally in Python, but RAPIDS has, each library has a C++ and a CUDA core. So there's a C++ library that underpins the Python library on top. And so what that means is we can build a C++, we can compile a C++ library and build a JavaScript API on top of that. Or we could build a Julia API, or really any language that you wanted. So this is largely a labor of love because I love data visualization and I want to be able to integrate my data visualization libraries with my GPU accelerated data science tools. So a couple of years ago, I started out on this little spike, and we've just got a couple people over the years, like 5 out of a team of 100 or so, that have focused on, okay, can we prove out that some of this stuff is actually possible to do in Node and Electron? But what I'm going to show you, none of this will run in the browser. CUDA does not run in the browser, and without some help from our friends at Google, it likely never will. So all of this is going to be running in Node, and it's possible to run in Electron. We have apps that run in Electron. But all of that because that has native, you can load native libraries, running from Node. So here's our little repo. You can go and you can clone it. I can help you set up and build it if you want, or you can npm install it. It's all available on npm now as of about a month ago. So let's get into what's going on. This is going to be a no slides talk. So if I lose anybody, I'm sorry. But this is all going to be code because I feel like code is the best way to show what's really going on here. But before we do that, I'm going to show you what we're actually going to start building, or what we're actually going to look at doing. I've got 3 demos here, and they're going to span the scale from starting from data ingestion, going all the way to visualization. So what you see right here is this window that popped up is an OpenGL window. So this window is a native platform window. We spawn an OpenGL context in it, and then we render into this OpenGL window. Well, now what's neat is this OpenGL window was started by Node, and this rendering is a CARTO base map using rendered with deck.gl. So how does deck.gl know about OpenGL? Well, that's where our libraries come in. We've got bindings to OpenGL that pretend to JavaScript as if they're WebGL. So you just go down the list, OpenGL and WebGL sort of one-to-one, and you just sort of provide a facade to the JavaScript layer that pretends to be a WebGL2 context. So what that means is you can do stuff like have a deck.gl rendering in OpenGL. And what that also means is that you can have native integration between your WebGL or your deck.gl APIs and CUDA. So your memory might be, you're doing this data science stuff and your memory might be in CUDA, and then you want to actually copy it without going round tripping through host memory. You don't want to copy it out of CUDA back into your CPU, RAM, and then copy that back into deck.gl. You want to do a fast GPU to GPU copy. Well, there are APIs at the native layer that let you copy from CUDA memory into OpenGL memory. And so we can take advantage of all those APIs because we're running natively and we have access to the native platform APIs. So that's why none of this will run in the browser, because you don't have that ability in the browser sandbox to do any of this stuff. But when you break out of the browser and you go into Node or Electron, you absolutely can, which is really cool. So this is just the first visualization that I want to show you guys. I'm just loading up the NYC roadmap here, and then I'm just mousing over this. But the visualization itself isn't really the cool part here. This New York City roadmap isn't the normal GeoJSON that you would have downloaded from the New York City website. This is actually the CSV that you would have downloaded from the website. And I'm doing that for a specific reason. I don't want to just do the easy thing, which is load in a GeoJSON file and give it to deck.gl. Deck.gl is really good at rendering GeoJSON files. What I want to show is a hard problem where you've got a data format in a weird format like CSV that you have to parse strings out of to get your X's and Y's. Like that's a really common thing in data science. You have a really weird format, and I need to parse it into something that I can use to visualize. And ideally, I'd like to do it very quickly. So that's why the interesting part about this demo isn't that I'm showing the roads here. It's that how I got these roads were by parsing this really weird CSV that New York City gave me. And so that's the first demo that I'm going to show you guys. And I'm going to gloss over a few of the details because I don't want to spend a bunch of time. But essentially, this data set right here is, I'm going to show you this CSV real quick, just so I'm not lying to you. This is the line CSV. And if we go here, full screen, this really has like the geometry and the multi-line strings with the XY positions that you would have downloaded from New York City. And if we go here where I'm rendering this visualization, so to do that stuff in OpenGL, what you do is we basically fake out JS DOM and we give you an OpenGL context, and then the rest is JS DOM pretending to be an actual browser. It's not. It's just an OpenGL context, but JS DOM makes it seem like an actual browser to deck.gl. And so this spawns a little window here, and then in the window we're importing this render streets class here. So the first thing that we do is we call this function to read the streets, and this read the streets function is the one that I really want to go through. But before we do that, what we're seeing right here is that the output of calling this function is going to be a data frame that has geometry in it. That geometry is described as a list of XYs. So it's a multi-line string for anyone who's familiar with multi-line strings. So then we take those streets and we do a little bit more magic, and then we copy them to host, and then ultimately we put them into a Mapbox overlay that just renders this GeoJSON layer. So I just wanted to show everybody this isn't magic. I'm not hiding anything. This is not anything that you couldn't do yourself. And actually, I'm showing the output of all my processes running my GPU right here, so you can show that I'm not lying to you whenever I'm actually doing this stuff. I'm actually allocating actual GPU memory in Node. So one more time, just open that up right here. And we can see the process. Over here, this is my node process, and it's allocated 287 megabytes of GPU memory. Cool. So what's this read streets function, and why do I care about it? Well, this is the function that's going to go and read our CSV that we got from New York City, and it's going to parse it out somehow into multi-lines. Like we've got multiple rows of this string data that it's relatively structured. It's got some spaces and commas in seemingly the right place with some parentheses. But like you've got this weird data format, and how do you do it? And most importantly, how do you do it fast without having to write like a single-threaded CPU implementation that's going to run regular expressions on your code or on your data? So this is largely, so cuDF has the ability to, cuDF is the data frame library. That's sort of the pandas equivalent of the GPU pandas equivalent from Rapids. And so what we got is the ability to read CSVs. We can also read other formats like Parquet or Arrow or Orc. There's experimental support coming for JSON reading. So that's actually really exciting soon eventually. So we can read a CSV and just trust me that this reads just fine. And then we're selecting out 2 of the columns, because really all we care about is a couple of the columns. And what's neat about the Rapids libraries for JavaScript is that we've implemented full TypeScript support. So we can optionally say this is a data frame that's going to have these 2 columns, and each of these columns is going to have a type. The type is going to have 2 columns, name and geom, and the types are going to be strings. So just so we can validate, we're going to print out how many rows we've got here. And then what we can do is we could filter this data set. There might be geometries that aren't multi-line strings. There might be geometries that are polygons, but all we want to do is show the roads. So we looked at our data set, we said, oh, it's got multi-line strings, that's the roads, that's all I care about. So let's filter out anything that doesn't match the prefix of multi-line string in our row. Well, I've got this fun function called matches RE, which is really weird. So here's my data frame, and it's got 2 columns, and the columns are both string columns. So I can extract the geom column, and I can run this function matches RE, which returns a Boolean of whether each value in this data frame matches this regular expression or not. So if it matches this regular expression, you'll get a true in that slot. If it doesn't match a regular expression, you get a false in that slot. And this is for every string in your entire data set. And what you can do with that Boolean column is then you can say, pass that to your data frame and say, filter out things that are false. Only keep things that are true in this Boolean mask that I'm going to give you. So we've been able to run a regular expression in parallel on every row in this data set on the GPU. And then we built a Boolean mask, and we filtered out the things that aren't relevant to us. So that's really awesome. Regular expressions, GPU accelerated regular expressions. So now we've got our multi-line streets that are filtered down. And now we actually want to parse out, given our streets, our geometry in string format, how do we parse that into something that's going to be an arrow format, ideally, that we could pass to deck.gl, like multi-line strings? Well, that's where we get really fun with the regular expressions. So we can say we can go and find all of our weird tokens, like all of our parentheses and stuff. We can start replacing them so that we can make it more normalized and match and make it easier. So let's just do a little bit of replace multi-line string, get rid of that. We don't really, now we've already filtered, we don't need to know that each row is a multi-line string anymore. We're also going to replace like open parens and closed parens, because we don't care about those. We saw that every row starts with open and closed parens, so that's really easy to get rid of. And lastly, it seems like they've got X's and Y's delimited with a space, and they've got pairs of X, Y's delimited with a space and a comma. So that's really important. We need to differentiate between things that are an X and a Y and things that are a point, right? So, and then the last thing we need to do is these are multi-line strings. So a road could have a single line segment, but it could have multiple line segments, and actually have multiple segments around New York City, because the same road might be there might be a dividing line between it. So we ultimately need to do a group by operation where we say we filter we get all the line strings for a road, but then we need to group them by which road they actually apply to. And if you're familiar with this data set, you might remember, if I just render this GeoJSON file in deck.gl, each line segment is actually its own distinct road to deck.gl. Like deck.gl sees each line segment individually, because the way this data set is structured is that they separated out all the multi-line strings into just a multi-line string of one segment, which is super frustrating if you want to do something like highlight the entire East Side Highway. you're going to get sections of the East Side Highway every time you mouse over it. And so we want to get rid of that. We actually want to make a data set that has all the line segments for the East Side Highway are going to be, in a single set of geometry. So, but we're going from strings into this nested list of lists data structure, which is super weird. But luckily, again, we can do some more magic with our data frame library and string parsing. So first, the thing we do is we come up with an ID, and we come up with we count the number of pairs in a line string. And then we compute a cumulative sum of all the pairs, and we use those as the values to scatter into an index buffer. And we're going to do a cumulative sum. So this is an exclusive scan operation for anybody familiar with GPU parallel primitives. So we're going to scatter the indices of these, where the line string starts and ends into an output buffer, and then we're going to put zeros in between them, and then we're going to sum all the way forward. What that gives us, that gives us a set of keys where for each individual segment, they'll have the same key. And what we can do then is we can do a group by operation and say, all of the segments that have the same key belong to the same multi-line string. And so that's what we're doing here is we're essentially coming up with that key column, and then we're coming up and we're flattening our points, splitting on our delimiter that we inserted earlier, removing the trailing delimiter because we're not context free. And then we're extracting the XY pairs into separate X and Y columns. So the neat thing is this geometry is a string series. We're splitting it on this delimiter and then partitioning that delimiter into things that come before and things that come after that delimiter. So I'm sort of glossing over what we're doing here. Ultimately, we get down to where we've got these lines. We've got points are this data frame of X and Y, and we've got our keys here. And our keys are actually technically one.
Mabliba is actually the only way to explain
operation. So you have the very last element, it's the total number of elements in the list. And so we can get rid of that. But then we group by our key column right here. And the neat thing is this group by operation will tell you the result of the group by. It says, oh, you're grouping by ID, and then there's certain things you can do whenever you're grouping. So you can collect all the values into a list. So where everything that has the same key would actually be put into a sublist together. And so that's this operation that I'm doing right here. So I've got this data frame that starts out as a data frame of ID and points. I'm grouping by ID because things that have the same ID should be put into the same list.
I really want you to know about this.
And actually, I'm sorting the values by ID after I collect them into a list. And then I'm just extracting out this points column just because I care about the list of X's and Y's.
Ideal.
So if I go back to this demo here, the really neat thing is that took 274 milliseconds. So on the GPU that I was going to bring, this is the backup GPU, the backup laptop. The GPU I was going to bring, that would probably run in under 100 milliseconds. And these are fully string operations on 120,000 rows. So that's pretty neat, I think. A bunch of regular expressions and string parsing, string splitting, and all that stuff. Ultimately, the point is if you have a lot of data like this, and you have just terabytes of this kind of data, a lot of people do. I know certain people in this room probably do. Is that you can write a relatively straightforward GPU transformation all in JavaScript or Python, and you can run through all your data in a couple hours, something like that. So that's cool, but that's not. That's not really doing anything like, that's just sort of doing string stuff, which is nice. Like string stuff is cool. But how do we do some like geospatial analytics or graph analytics? Graph analytics is the next one I want to do because it's sort of the next one that's not. I'm going to come back to geospatial after the graph one. So the next problem I've got is purely a graph analytics problem. I've got this graph.json file, which is about 500 megabytes of just X's and Y's and or like sources and dests. I've got this from I can't remember where this data is from.
You have to make sure you.
And it's so big that VS Code doesn't even really want to open this file, but it doesn't matter because we don't need to open it. So what can we do here? We could read this file as a JSON file. We could actually just open the file in JavaScript and do JSON.part.
It's pretty fast.
And I'll actually do that.
So there are some limitations, right? So if I, for instance, here This is specified.
So
50,000 miles.
right here, this is, I'm running this test read function that I've got defined right here. So I've got this function called read JSON and CPU. I'm just going to do the basic normal thing, read the file from the file system, call JSON parse, then construct, the XY, the size, the color buffers by, just constructing the typed arrays here, and then returning all those back out to the user. Which
my decision how
not that bad. If we look right here at how quickly it ran, we were able to parse. So read that JavaScript file, that JSON file from from disk in about a second. JSON parse only took about 8 seconds. Not bad. Creating the buffers is actually pretty quick. So total time roughly almost 9 seconds. Not bad at all.
So imagine that we will have this.
I can do the same thing on this relatively old laptop GPU in about 5 seconds here. Which, if this were the GPU I was going to bring, which is a new one, it would have been 1 second. So that's what we're seeing right here. But what's neat is that if we've got this relatively structured JSON file, you can parse this file using just some similar string operations like I was doing before when parsing the CSV. You know that there's only a certain number of keys. You know that if you've got an edge list, it's going to be an array. And so we can actually use this operation called multi-byte split, which will split the string and run string operations in parallel. So it'll look for the same delimiter in parallel on the entire GPU and then return you all of the places where that splits. So essentially we read this JSON file from the bottom up, right? And so we start with the last thing we want to read about it and find where it starts, and then read the value, and then we'd use the stuff before to continue reading our JSON file. So all that to say, reading this JSON file still from disk only took a second to load. That's not going to be any different. Unless you're using something like the GPU direct storage, it might be available in a server GPU. But reading out these values from the actual file, took roughly 1.6 seconds for the noted edge list. And then reading out the JSON file options, took a little bit more. So that's not all right. So I'm going a little over time, so I'm just going to skip ahead here. What we want to do is we want to actually render this and show. So we're going to use cuGraph here to run. This is the graph analytics library, and we're going to run graph layout on this graph that we've just parsed from CSV. So this is running a physics simulation on the GPU, and then copying those buffers into OpenGL using that CUDA to GL interop I was talking about before. And it's actually really neat because the physics here is super messed up, but it looks cool. So that's really all we care about, right? But we can see, if we go here, one of the other nice things is we can print out this data and it automatically formats nicely. So if anyone's ever had to print out tabular data, it always sucks. So we implemented GPU accelerated printing into the console or something, because it's super common in your data science workloads to want to do this. All right, so the last thing I want to do is jump back to a geospatial demo. So this NYC taxi data set, something that's really common is we want to be able to take a lot of points and do like point and polygon tests on them, right? That's something that ideally should be good on the GPU. But we don't want to do like a naive point and polygon. We want to use like a more intelligent data structure like a quad tree to do, spatially filter out all the points that, aren't in a certain area. So I'm not going to get into the details of what we're doing, but Rapids has, as far as we know, the fastest quad tree building algorithm in the literature when we implemented it. So again, I'm using deck.gl here just to render out the polygons of all the taxi zones in New York City. And then I've loaded because I had to get the data set size down to what could fit in this machine. It's only about 110 million points of the New York City, pickup and drop off locations. But what I'm going to do is when I mouse over a taxi zone, I actually want to filter that data set and only give me back the points that are in the polygon that my mouse is over. And this isn't, like I said, this isn't smoke and mirrors. This is happening in real time. As soon as I move my mouse, it's filtering out only giving these points back to me. And then I'm using the GPU to GPU copy from CUDA into OpenGL to get these into deck.gl for rendering. So if we look back at, I've got the times here. So you can see it's taking about 18 milliseconds to do a point in polygon and 2.7 million points, or 2.8. And so that's pretty cool. And I just wanted to show that off. So I know I'm over time. I don't want to go over for anyone else, but does anybody have any questions? Or you can always talk to me after this. About debugging? Ah, yeah. So if you have some code running on the GPU, it's running on like 100 threads, how do you go about debugging it? That's really a problem for us, not you guys, ideally. So if you're us, then yeah, we build the code from source. We connect to it with CUDA GDB. We breakpoint inside the kernel, and all of that you can definitely do with the CUDA ecosystem. If it's you guys or me building stuff with this on top of it, it's not going to be so much correctness of the underlying algorithm, because we have that pretty well figured out. It's going to be more like, oh, I thought the algorithm was going to give me this, and it's actually giving me something else. And that, yeah, it's kind of a normal thing in data science. You just like verify the output. You take a slice of it. If it's doing what you think it should, if it looks good, then you go with it. If not, you're like, why is this returning NaN? There's probably a NaN in your code somewhere. But the neat thing about it is that if you can get a lot of that correct, the thing that we went and did was we said, okay, we're going to make it easier for you to know when you're. One thing with Python, right? You're always like, oh, I've got a data frame and I'm doing a join with another data frame, and that's going to produce like a result data frame that's got some combination of the columns from the left side and the right side, but like who knows what they're going to be named, and you might have a typo in your code somewhere, and so you thought the column was something underscore X, and really it's something capital X, like all that kind of crap. So we use TypeScript to tell you, no, you've actually got a typo here. This data frame doesn't have a column named that, or like it's not typed that. It's a string column and you're trying to do a float operation on it or something like that. So typically TypeScript now will save you from a lot of those. I've found personally doing all these demos, I found TypeScript to be really good for that. If you want to actually write some GPU CUDA code, then you have to really get into the CUDA ecosystem. But if you want that, we've got that whole development environment set up for Node Rapids, and it's all containerized, so it's not super hard to work in, and I can help you get that set up too.
Really cool stuff. I think you mentioned in the beginning that it seems to run in the browser, right?
No, it doesn't run in the browser. Now, here's the trick. If you want to do something like have a server, right, a node server or something running in the background, you could then say have an API, right? Like you could have an HTTP REST interface that will take the code and take the data frame that you've got on the GPU on the server, save it out to arrow format, stream that down to the browser, and render in the browser the binary data that you sent over via arrow, right? But this code, because CUDA will never run in the browser unless our friends from Google want to help us. I wish it would, but it won't. And so you can build a client server model, and that's why like Arrow IPC is really good for that. So you can take your data that's in the GPU, and we can very efficiently get it into Arrow format because the format's almost identical. And then we can stream that over the network in chunks encoding all the way to the browser. And you can keep, like that's what we did at Graphistry to do these 60 frames a second really fast GPU accelerated layout with browser rendering. Or what you could do as an alternative is these GPUs nowadays have video encoders in them. So I don't know if you've ever tried to use your video encoder for FFmpeg or for streaming if you're a gamer, but these video encoders all exist on the GPU. It's like $1 or $2 of like every GPU you buy is like licensing for video. So you could actually render on the server and then stream out to the browser a video of what's being rendered in OpenGL on the server. And then the browser, it could be an iPhone. It doesn't have to be a big fancy GPU box, because really all it's doing is streaming a video over WebRTC, just like I'm doing on Zoom right now. So, that's accessible to any device, and you can do this. That's sort of the GeForce Now model. You could do GeForce Now for data visualization if you wanted to build that kind of service. So that would be using the GPU for compute, for graphics, and for video. And so you'd really be getting a lot of value out of your money there. But I didn't want to show that off. So we got to go.
Sorry, it's a question from Andres Moreno.
Okay.
So he says, what do you see in the future for JavaScript ecosystem support?
What will you see in the future for JavaScript ecosystem support in CUDA or Rapids or? Okay. So like I said, this is Rapids is largely Python focused. We think there's a lot of people in JavaScript that could really benefit from this and really start to use it and might like it. But we don't know that. And so what we need to hear feedback from you guys or just get involved. Like, this is a super experimental project by me and like 3 people. So what we need other people to show interest, and then that sort of tells people at NVIDIA, hey, this is something worth pursuing, and this is a community that it's worth building bridges to. You talk to any GPU person traditionally, and they think dynamic programming languages, their head explodes. And on the flip side, JavaScript people don't know a lot about what's going on in CUDA because there's not that outreach. So this is us sort of trying to build that outreach, and if you want to see it expand, then just get involved, whether that means emailing me or filing issues, or whatever it is. Certainly, if you want to contribute, I would love that, and I'm happy to get you started.
Quick question: does it support basically all the deck.gl layers at this point?
So does it support all the deck.gl layers? So the OpenGL, you're talking about the OpenGL rendering thing? So yes, I actually ran the deck.gl test suite on the OpenGL, on top of the OpenGL thing, and it seems to pass. We've got things like the TensorFlow JS test suite that we run, and in most of things in that seem to pass. So we've got a conformance suite that seems to work. Getting the mapping layer was really fun because Mapbox and MapLibre do some fun stuff in the background with workers. So we had to mock a whole bunch of stuff about workers to make that work, but it's working now. So really, the JS DOM layer is really just a shim to be able to let you do GL stuff. It's not trying to be a browser. We're not trying to render text or anything. If you want to do that, please use Electron. But what we're trying to do is, this is for, if you do want to do that video streaming thing, or you do want just server, you want to validate stuff on the server, we want to have this layer too. All right, we good?
Thank you.
Cool, thank you.